Another quantity that helps us to measure the propensity of molecules to undergo collisions is something called the mean free path. So let me define what that is. The mean free path is basically the average distance that the molecule will follow or molecule will travel in between collisions. All right, so this tells us something about how much of the time they actually spend in collision versus how much of the time they're not engaged in collisions. Now, last time we learned that the collision rate for these molecules could be written in the following way. It's the square root of 2 times the number density times the cross-sectional area times the average velocity of the molecules. And this is going to give us a result that is going to be in units of collisions per second. So if we want to get a handle on how far it travels during this time, we need to have an idea about how long it's spending in between collisions. So one way we could do this is just to say that the time between collisions is simply going to be 1 over the collision rate. Okay, if this is giving us collisions per second, the inverse of this would be seconds per collision. So that tells us how long it is in between these collisions. So that will give me a result that looks like this: 1 over the square root of 2 rho sigma times the velocity, the average velocity. Okay, but what I want is a distance, not a time between distance. Well, the way I would ordinarily do this is I would say that rate times time is equal to distance. So if I want a distance, I simply need to multiply this time between collisions times the rate. But the rate is just the average velocity of the molecules. So if I multiply this by that average rate, I'll end up with average rate over z collision is going to give me 1 over the square root of 2 rho sigma. And this result is something that we identify as the mean free path for the molecules. Okay, so it's a fairly simple result and fairly straightforward to get to it. Now, what I want to do is, since this is a relatively easy result to get to, I could make this a 30-second video, or I could tell you a little bit more about what sort of typical values one gets for these things. So let's take a look at that. All right, average number density for molecules, so this is number of molecules over volume, would be something like the number of moles times Avogadro's number divided by the volume. But this number of moles over the volume is something I can use the ideal gas law to tell me is equal to P over RT. Oh, I've made a big mess of this. Let's grab our eraser, erase all of that, and now we can do P over RT. Okay, so if I use something like 6.02 times 10 to the 23rd for Avogadro's number, I use 1 bar for P. I'm going to use 300 Kelvin for T. So just room temperature. I'm just looking at standard conditions. And I need to divide by R. So I'm going to have 1 over 0.083145 liter bars, etc., etc. So what I'll end up with is the number of particles is going to be something on the order of 2.4 times 10 to the 22nd. And that's going to be in molecules per liter. Okay, well, liter's pretty big for molecules, so but it's not as big as the metric system would have you do it. What we really want to do is convert this to meters cubed, but it takes 1,000 liters to make a meter cubed. So when I make that conversion, I'm going to end up with a number density that looks like 2.4 times 10 to the 25th molecules per meter cubed. Okay, so that's one of the numbers we need. I didn't specify last time. I talked about the cross-section of a molecule, but I didn't say anything about how big it is. I'm going to simply tell you that it runs from about 1 times 10 to the minus 19 to 1 times 10 to the minus 18 and that's in units of meters squared. Remember, it's got a unit of area. Since molecules are very small, we expect it to be a very small area, so it's 10 to the minus 19 to 10 to the minus 18 or so meters squared. So we'll take the average of that. We'll just say 5 times 10 to the minus 19 meters squared is roughly the molecules that we're going to do. The last thing we need is an average velocity. And if we were to plug some numbers into 8RT over pi times the molecular weight in kilograms per mole, what we would find is that an average speed for molecules typically ranges between 200 and 600 meters per second at normal temperatures. Okay, the lighter molecules would have the higher end, the heavier molecules would have the lower end. All right, so we're going to be looking at velocities that are roughly in this range. We're going to be looking at cross-sectional areas that are roughly in this range, and we're going to be looking at number densities that are roughly in this range. So what do these things end up looking like? Well, when I plug these numbers in, what I'll find is that in fact the collision rate for molecules, so this is, remember, it's under relatively standard conditions, the collision rate is going to end up being something on the order of 3 times 10 to the 9th, all the way up to perhaps as much as 10 to the 10th collisions per second. All right, so there's a lot of collisions that are happening each and every second. And, this is for molecules that are in the gas phase at about 1 bar of pressure. What about the mean free path? Well, I would find that lambda in this case is going to be roughly 1 over that, but when I plug these numbers in, I'll end up with a rough number that looks something like 6 times 10 to the minus 8 meters. Okay, so not a very long distance, but when we compare it to the distance, or I should say the size scale of a molecule, it turns out that this is roughly 200 to 300 times the size of a molecule. So in other words, if you were walking down the street in downtown and you had to walk about 4 to 6 football fields before you would run into another person, you would consider yourself lucky, one, but it'd be a pretty long distance. So what you should consider is that molecules have to go a pretty long distance relative to their own size scale before they have a collision with another molecule. The other thing that you should know is because of the time between collisions, molecules undergo hundreds and even thousands of vibrations and rotations between collisions. So there's a lot of time for them to randomize energy within themselves and become, if you will, internally thermal.